طيب بسم الله الرحمن الرحيم. So we're still in part 1, chapter 2, still talking about symmetric encryption. We talked about some symmetric encryption techniques like this, triple this, and AES, and the difference between them. Talked about the fizzle structure and how we can use that fizzle network as the basic building block for this and triple this. But then AES changed that revolutionarily to try to speed up the process using some matrix multiplication and more software optimized implementation. Then we started to talk about pseudorandom generators, pseudorandom number generators. And these are very important, as we will talk today, that these are also the building blocks for stream ciphers, not for block ciphers, for stream ciphers. So as we said before, the pseudorandom number generators can be done in two different ways. One is to design a specially made algorithm to generate random number based on a seed value. Okay. Of course, there is the random number generators in general, which are not based on the seed, and for that we take any random source from the environment. We talked about an example for this, like wireless channel, for example, is a source of randomness, and we can take it as a source of randomness and create some random sequence. Okay, not based on a seed in that case, but pseudo-random number generators are based on a seed, and you can think of the seed similar to a key. Okay, it's sort of a key actually. So based on using that seed and the random number or the pseudo-random number algorithm can in fact generate some random sequence based on that seed. Okay, and of course this random sequence has to fulfill the two conditions we talked about. The randomness here talks about the fact that you need to have a random sequence which has uniform distribution. And what that means is the probability of having any pattern is actually the same. So the probability of ones equals the probabilities of zeros. Okay? Even if you take 2 bits, the probabilities of having these 2 bits is similar to any other bits. Okay? So that's a uniform distribution. Okay? So that's very confusing to any attacker, because if you have anything other than uniform distribution, chances are the attacker can try to play or to try to do some traffic analysis to the pattern with higher probability. Okay? Because if you get that, then you can break the communication faster, right? But if there's no higher probability pattern in your random sequence, the attacker will not be able to do anything other than brute force technique. And that's what we want. Brute force is the worst case, because nothing is unbreakable. We know that. Okay? But at least if we have the attacker only using brute force, then at least we delay the attack for as long as we can, and in that case the time that the attacker will take will be actually, in terms of value, will be much bigger than the communication that he's trying to break. So in which case, the attack will not be feasible for any attacker. Okay? Type. So this is the purpose-built algorithm. Of course, one example of this purpose-built algorithm is the encryption technique itself, because the encryption, instead of the seed, it takes a key, and we know that with the key and with any input text or plain text, we can get a ciphertext that looks random. Okay, and in many cases, the ciphertext is also fulfills that two conditions: the randomness and the unpredictability. Okay, again, the encrypted text in many cases has no correlation to the input text and has these two conditions fulfilled. So with that pseudo-random number generators, we can, in fact, design our stream ciphers. Stream ciphers, unlike block ciphers, the plain text itself takes any arbitrary size. Okay, it's a stream from the name. It's actually a stream that can take any size, because as we talked in DES, for example, the key has a certain size, and the input text has a certain size, right? The input text is 64 bits. You cannot have, if you have a text that's more than that, you have to chunk it in blocks. No, you have to chunk it in blocks, okay? And then take each block and perform the block cipher, right? But with stream cipher, that's not the case. The plain text can be as long as possible, and you have to have the here. The modification here is that this pseudo byte generator will generate a random sequence as long as you want. Okay? Unlike block ciphers. So block ciphers, you put a plain text, okay, with a certain size, you get an encrypted text with the exact same size, right? So here it's different. So there is a pseudo-random number generator that generates a key stream sequence. Here, the output here is a key stream sequence of as long as you want. Okay? And then here, what we have here is the normal Vernam cipher. We just XOR to the incoming stream sequence, byte by byte. So in fact here, you can generate one random byte, and then XOR it with the first byte, and then you generate another byte, and so on. Okay? So this way you can continue this process forever if you want. Okay? So that's the difference between the stream cipher and the block cipher, which uses fixed size block and fixed size key. Okay, here the key is fixed, but the output text is not fixed, or the plain text is not fixed. Type. Some properties here, if we talk about the block ciphers, something you will find, and you will see this in the assignment that I posted today. So you will have a very clear observation that stream ciphers, they are more protective or more resistive to channel noise more than block ciphers. And what that means is, if you have a transmitter, this is a transmitter, and this is a receiver. Okay, if that transmitter uses stream cipher, okay, for a stream of bits, and this stream cipher, okay, will produce an encrypted stream, okay, of any arbitrary size. Okay, so if you move that across the channel, this is the channel. Whatever that channel is, if it's wireless, wired, whatever. Okay, if you have any source of noise or any corruption to this text, okay, not even by the attacker. It's just a normal error that happens on the channel, not necessarily an attack. Okay, so chances are the stream that you recover here will be highly correlated to the transmitted stream in the case of stream cipher. Okay, and the reason for this is obvious. It's obvious because, as you can see here, this XOR, okay, preserves the stream, and if there is any error that happens in the middle of the stream, okay, to the encrypted plain text, to the encrypted text, okay, this will affect only that part, because what you do is simple XOR all the way, right? However, for the case of block ciphers, you lost the whole block. Any kind of alteration, any kind of small error, even 1 bit in the block, you lost the whole block. Okay? Why? Because the block cipher is based on continuous and round over round of permutation and transposition, which will make the cipher text as a complex combination of the input text. So any one bit changes in the block, you lost the whole block. Okay? But here that's not the case, and you will see this in the assignment. Okay? Type. However, in terms of security, which one do you think is more secure? The block cipher is by far more secure, of course, right? And as we have talked before, there is a very important property here for the Vernam cipher. Whenever you have an XOR, okay, you can observe, or you can easily say that, okay, so if the cipher text is actually the key XORed with the plain text, and the plain text in that case is this, and in that case, if you have the attacker using the known or chosen cipher text only attack, okay, in that case, the only thing that you have is this, is the cipher text, okay? So, as we said before, there is a clear proof that if the only thing you have is the cipher text, the only way you can guess the key is using brute force. Because you don't have any plain text, okay, that corresponds to a particular cipher. However, if you happen to have a C1 equals to K XORed with P1, if you happen to have a known plain text, only one known text, okay, then it becomes a trivial problem, because the key is in fact a C1 XORed with P1. So only by knowing one single plain text, you can break the communication. That's the sensitivity of this. Okay? This is the main sensitivity of any Vernam cipher, is that in normal cases, if you don't have a plain text, it is secure, but if you have only one plain text, you can break the whole communication. And again, the proof for this follows like again information theory, based on the fact that the probability of a key taking certain value, key ki, for example, given C, given that you know C, okay, is in fact equivalent to the probability of k equal ki, which means that having C only does not affect the probability in any way. Okay? Having C only will not give you any information. But having P, only one P, will allow you to break down the communication. You have a question? This is for the stream side. Any kind of XOR cipher. Any cipher that uses plain XOR. Of course, in block ciphers, we also use XOR, but as part of the fuzz structure, which contains so many other things, right? So the block cipher is much more sophisticated. So it's not based purely on XOR and that's it. It's actually based on many rounds of permutation and transposition and so on and so forth. Okay? The key, the way that you generate the key is a long story. The way that you generate the key is a long story. Here, the way that we generate the key sequence, okay, is by using pseudo-random number generators. So, but this key, by the way, is here, is this key sequence, okay? So the way you generate the key is here for the stream ciphers, typically using a pseudorandom number generators. For block ciphers, you can use some kind of a key server or a key distribution server. We'll talk about this later. There is a protocol that you have to use in order to generate these keys, share these keys with the participants and so on.
My question was, is that key you generate it and you have the option to generate it in any link you want, but at the end it is a fixed key. So you know that key is like that link.
Well, no, again, we'll talk about this because it should be fixed for a duration of time. As we said before, nothing is unbreakable. So if you leave the key fixed for a long duration of time, you increase the probability of attacks, because even if you use brute force, okay, you can still break the communication. So if you leave the key for a very, very long time without changing it, chances are you will be attacked.
Only flexibility in a way that you can generate any key with a specific link, but at the end the key it is
here. By the way, here also the key is fixed, and we'll see that.
Yeah.
The key here, the key size is fixed. What's not fixed is the plain text. The plain text can take any arbitrary size, and we'll see. But the key is still fixed. The key has a fixed length. Okay. For the stream cipher, yes. And for the block cipher, it was also fixed, right? Fixed size, not fixed value, fixed size. Okay, fixed size. So for, as we said, for this, it's 56 bits, right? For triple this, it's triple B 56, which is 168. And for AES, it starts from 128, and it may go to 256 in some cases, okay? Another property which is also as important here, which we did not actually talk about in block ciphers, which is the issue of synchronization. So supposedly, if you because we're talking here about pseudo-random number generator, huh? It's not completely random, right? So if you use the same seed, here and the same seed here, okay? So these two random sources or pseudo-random generators, they're supposed to generate the same key sequence, right? But if there is any misalignment in one byte, this is a lack of synchronization, in which case the byte that you generate as a random sequence to XOR with the plain text is not going to be equal to the byte that you generate on the receiver side because of this misalignment. And that could happen easily if we're talking about arbitrary size text, right, that can go on for a very, very long time. So you can lose this alignment easily, in which case you break the synchronization between the transmitter and the receiver. And this is a quick announcement. This is a bonus. If you do it in the assignment, you can get a bonus mark. Yes. You can do it easily. You can just generate the same random sequence, but just break the alignment for 1 byte or 2 bytes and see what happens. Okay? You can easily do that. And that can happen in practice. Okay? Synchronization in general is a very, very big problem in any communication system. Okay? Which may happen easily because of the fact that the clocks that you use on both sides are not identical 100%. So you can lose this synchronization at any point of time. So any questions so far? So these are some of the properties of the stream cipher. So now, which is here. Okay. So now the encryption sequence should have a large period. Okay. And the period of repeat, the bigger or the longer this random sequence is generated, the more difficult it is to break it. And the key stream should approximate the properties of a true randomness and also a unpredictability. So if we take a long stream sequence, okay, let's say a long stream sequence of ASCII characters. ASCII characters, they can take the value from 0 to 256, right? Okay. So if we take a very, very, very long random sequence, just take the probability of having ASCII character 0, probability of having ASCII character 1, 2, 3, 4, all the way to 255. Calculate the probability of having any of these numbers. You should always find them very, very close to each other, which is 1 over 256.
Theoretically, right?
Theoretically, of course, because in practice, of course, it would be plus or minus. That's fine, but you should have. That's what we refer to as a uniform distribution. Uniform distribution. So the probability of having any of these ASCII characters in a very, very long random sequence is going to be pretty much the same. Okay? So this way, it's true random. Okay, and now, the second condition is unpredictability. Unpredictability talks about the fact that if you take any part of it, you will not find any correlation. So the fact that you have, for example, 2, 3, okay, it doesn't correlate in any way that the block after this, you will have مثلا 3 and 4. Because you can easily say any block, any future block is the previous one plus 1, something like that. So if you have any kind of correlation between the different parts of the sequence, it will be predictable. And in that case, you can use a very, very simple cryptanalysis to break it. And that's not what we want. What we want is to always force the attacker to use brute force. طيب. So this is what's explained here. So the pseudo-random number generator is conditioned on the value of the input key. So the random sequence is based on the input key or the seed. We called it the seed last time. Okay, so those are the same pretty much. To guard against the brute force attacks, the key needs to be sufficiently long, and we'll talk about this because as you can imagine, the key itself is fixed length, right? But the random sequence is very long. Okay, so if you get a very, very, very long sequence as a function of the input key, and the input key itself is small, okay, chances are after a very, very long time, you will start to see some correlation. You'll start to see some repeated patterns, no matter what you do. So, you can imagine that? So, after some time, you will see yourself, you have to repeat certain patterns. Okay? So, in that case, that's an alert for you to have to go back and change the key or change the seed. Okay? That's why it's always advisable for any random number generator not to use the seed for a very, very long time. If you use the seed for a very, very long time, your random sequence will become, after some time, after a very long time, it will become predictable. It will become predictable. Okay? So based on experiments, they found that, typically the key size should be around 128 bits or more. So using 128 bits of key, you can generate a random sequence of megabytes of random sequence. Okay? So a stream cipher designed in 87 by Ron Ravers for RSA security. It is variable key size stream cipher with byte-oriented operations. يعني byte-oriented operations you generate 1 byte of random number at a time, and then you XOR it with the incoming byte from the input text. And you keep doing that, and we'll see the process for this RC4, how it generates bytes repeatedly, and you can repeat this process, theoretically speaking, forever. However, this forever is questionable because, as we said, after a very, very long time, you will start to generate some predictable patterns, in which case it's going to be easily breakable. The algorithm is based on the use of a random permutation, and we'll see how this is done. And is actually used in SSL. It's used in TLS standards, اللي هي Secure Transport System. And we'll talk about this in part 2. In part 2, we'll start to talk about the major standards in terms of security services in every single layer, in all the 4 TCP/IP layers that you know about, starting from the application layer, transport layer, network layer, and data link layer. And it's also used for wired equivalent privacy, web, and I think recently it was deprecated because of the fact that, especially for wireless is a broadcast environment, right? Which makes the passive attack very, very easy because it's wireless signal, right? So anyone can read it, right? The problem with the web or the Wi-Fi, WPA in particular, is that you can read that plain text in the beginning of the communication. You can get that plain text easily. And as we said, because we are using Vernam cipher, this XOR cipher, if you get one plain text, you can break the communication. Okay? So that's why WPA, especially for Wi-Fi, has been deprecated because of this RC4. Okay?
WPA was discontinued because of the poor implementation of RC4 rather than RC4 itself.
Yeah, you could say that, yes.
Because of these IDs and that could be uncovered if you do injection.
That's true. So the implementation itself can make the guessing of that plain text easier, in which case you can break it. Okay? But some other implementations can be more protective. Yes.
Sorry.
تفضل.
Isn't the
طيب. So the RC4 is based on these these steps, and the important thing here is that you have a key. So you have this key. This key is fixed length, and it has a length of key length. Okay. From that key length, you will generate this T vector, which is a fixed length of 256, which corresponds to all the possible ASCII characters. So you have a S vector, okay, which is fixed. You have ASCII character 0, 1, 2, all the way to 255. Okay? So the length of that is 256 characters. Okay? And then from the key, first you have these 3 steps. 1, you have initial state of S and T, and this T is another vector that gets generated based on certain permutation, and it's actually a straightforward permutation of the key. Just by simply taking the first character here, and the second character, and after the key length, you just repeat, you cycle. Okay? So it's actually 256 mod key length, which means that the first character here, you put it in the first character of T. Okay? And the second character in the second character, and so on. After you finish key length, you just say, you repeat the same cycle again. You keep repeating that until you finish all the 256 characters. So now you have the S vector, which is fixed from 0 to 255, and you have the T, which is based on the key. And the key here can have any arbitrary value, of course. And it's just repeated multiple times. The length of the key is anything less than 256. But T has a fixed size of 256. Okay? So this is step number 1, or step A. here, which is a initial state of S and T. Okay? Second step, we will do one fixed size permutation. One fixed size permutation, which means that for each element in T, we start with element number 0. Okay? We need to find another element, okay, to swap the value of this with the value of the other A character. Okay?
Some other T.
A?
To swap it with some other T.
Some other T. This other T is indexed by J, which J starts from 0. Okay? So J, when it starts from 0, the new value for J will be the 0 plus S of I. So at I equals 0, this will be 0. Okay? And Ti. Okay? Ti is not 0, by the way. Remember, Ti is based on the key. Okay? So it's not necessarily 0. Okay? So Ti will have any value. Okay? So J will be 0 plus Ti, which is based on the key. So you will get the value of J, and then all you need to do is just to swap T0 with that value of J. Okay? سلام. في محاضرة عندك؟ Yeah, in T, yeah. So the idea here is to try to take T and perform certain permutations on it. Okay? That's the main idea. So we'll take each item in T one by one, okay? And then we will select another item deterministically. This is not probabilistic. Deterministically, right? And that's why it's pseudo-random number generator. So supposedly if you have the same key, you will generate the same random sequence. Okay? So you will do some arbitrary permutation using this. But in this step, it's fixed size, which means that we will go one round through each of the items in T and swap it with another value. And we'll keep doing this. And of course, the addition here is modulo 256. All the additions here are mod 256. واضحة دي, huh? Go ahead.
Isn't it that in our RC4, maybe I'm wrong, correct me, that master key that is shared between the sender and recipient is used to generate something similar to one-time pad, which is one-time key using these IDs that are sent to the plain text and used to create this one-time password? Or that's some other algorithm?
No, that's different. That's different. Because this
I know WEP had a problem with RC4 because of the way it distributed these IDs. ID is a great
yes,
great
initial vectors, the initial vectors, yes.
Initial vectors are used in combination with the master key to create the one-time keys in order to encrypt. Right. This is a little bit different what you're showing us.
Well, this does not use IV. The basic algorithm itself does not use IV. We'll talk about some other techniques after that, which uses IVs. But I can imagine, based on what you say, that there are multiple implementations of RC4 which might, in fact, use some IVs in this process.
Because I know that stream cipher like RC4 was compared to one-time pad, and because of the way where you can generate these one-time use keys.
There is a difference between WPA and RC4. WPA is based on RC4.
Yeah, sure.
Right. WPA itself is based on RC4. But when I say based on RC4, it's like this based on the Fiesel structure. But it's got other things on top of that. So maybe WPA uses the engine or the core as RC4, but it uses IVs in a certain way on top of RC4. Okay? in which case they compare it with the one-time pad and so on and so forth. But remember here, it's not to generate password, although, of course, password is like any other, we can consider it any other random sequence. But this is used for communication in particular, and it's used to encrypt stream of information between a source and a destination.
What I meant is like if we shared already master key, right?
Between source and the destination.
Source and destination. If the same ID is shared with both of the parties in clear text, during the generation of the so-called one-time use key, they will use the same keys because they have the same master key.
Right.
So you avoid this problem of reusing the master key. You can keep it for longer.
I see what you mean.
Yeah.
Okay. So you can change the key every now and then arbitrarily.
Without changing the master key.
Without changing the master key, yes. So we'll talk about this concept, by the way, a lot when we, in part 2, when we talk about standards. In standards, they use that concept a lot. And instead of just changing the actual value of the key, they have like sort of a master key, and from this master key, they generate multiple keys at different times, based on some IVs and some combinations. But that's, we'll talk about it later, inshallah. Anyway, so the second step, as I said, go ahead.
Just real quick. So let's assume that our key content is 456. So
Right.
T would be 456, 456, 456.
No. Well, the key itself is 456 only.
Yeah,
Okay. Yes. So T here will be 456, 456, 4.
Until we...
Yep. Yes. Okay. So the second step here is, as I said, fixed size permutation, fixed number of steps for permutation. The number of steps here is 256. Okay. We just need to go through each of the values in T and swap it with another value based on this very simple formula. Okay? SI here is fixed, but TI is not fixed. TI is based on the key. Okay? Type. Once we do this, in the third step here, in the third step back, we generate stream generation. Stream generation here is of any size. If you look at the code in the book, it will be like while true. It's not bad for I equal from 0 to 56 to 55. No, here it's while true. Okay? So you can do this step as many times as you want. Okay? This is the main difference. And here we go on the J here equals J plus SI, and again we swap. But we keep doing this. We keep always doing this. And J here is the value that you will take and you will up. This is the random byte that you will XOR with the incoming value from the plain text. And you will keep doing this. So the first permutation is dependent highly on the key. The second permutation, C214. The second permutation now, خلاص, the dependency on the key has been accounted for, and now we generate as many bytes as we want, okay, using this second step, اللي هي stream generation. واضح كده؟ T yes. T equal SI plus SJ. Yeah, so that T is the value that T is the value that we generate, and we XOR with the byte that's coming from the plain text. Okay. So the pseudo-random number generators have now been used to generate a random sequence to facilitate the stream cipher. So in this chapter 2, we talked about the symmetric encryption. We talked about three major categories of block ciphers, or three major techniques of block ciphers, and we talked about one simple example for stream cipher, which is RC4. All these four techniques, they will be, you will have to experiment with them in the assignment. Not only that, there is a part here that I kind of, removed, which is the operation modes. So for operation modes, we will talk about the concept of blockchaining and stuff like that in other techniques. So there are three operation modes. Operation modes are nothing but, you perform the same symmetric encryption, but using different pipelining, different chaining of the blocks. So instead of generating the ciphertext based on one plain text, no, you have to do it in a chained fashion. So you will do that in the assignment as well. So I'm removing it here, but in the assignment you have to go back and read it anyway. Okay, but only for experimental, for hands-on. But it's not going to be part of the exam, of the theoretical exam. Any question about this? MATLAB. I tried to look for anyway. So we'll start now. Chapter 3. Chapter 3 talks about public key cryptography and message authentication, and it's actually an interesting dimension that this book takes, unlike any other book. So because in many other security books, you will see that public cryptography is discussed in the same place like symmetric cryptography. Because the only difference is just to use two keys instead of one key, right? So looks like it's kind of similar. But here this book actually takes a different angle. It talks about public key cryptography as part of message authentication. Yeah, so it's functionality oriented. Because when we discuss this, you will okay. So here, the book tries to discuss public cryptography as part of message authentication, because mainly this is what it's used for, as we would see. So for message authentication here, we know that the encryption itself protects the message against passive attacks, right? So that's a fact, we know that. Confidentiality talks about the fact that we hide the information so that no one can eavesdrop this information. But if a person tries to do any kind of active attack, like for example, man-in-the-middle attack, I impersonate myself as the source or as the destination, and I try to inject some text that corrupts the communication. Confidentiality would not help in that case, because I can take the same ciphertext, okay, and embed something in the middle and send it back to you. Okay? If you accept it, you will decrypt something that has nothing to do with the input text. And as we said, especially for block ciphers, it's very sensitive to any alteration, to any modification. So if I change the ciphertext by only one bit and send it back to you, and you accept it, then it will corrupt the whole communication. So the key is you accepting it, okay? So you're not supposed to accept anything that's not authentic and it's not coming from an authorized source, okay? So in which case, confidentiality is mandatory, but it's not sufficient for secure communication. So we need more than that. We need to authenticate. Authentication here has two levels. You authenticate the communication with a source, okay? That's what we have referred to as peer authentication. So we need to authenticate the communication itself. So we need to identify each other, okay? And then each single message has to be authenticated. So there is message authentication as well. So just the fact that I identify that you want to communicate with me, that doesn't mean that every message that you will send, I will accept it. If it's really coming from you and I can authenticate that message, then it's fine. I can accept it. Okay? So message authentication is the procedure that allows communicating parties to verify that received messages are authentic. So the two important aspects are to verify that the contents of the message have not been altered and they are authentic. معناها it's coming from an authorized source. And not altered معناها the integrity of the message is preserved. Okay? So if I take an encrypted message, but then I put something in the middle and send it to you, well, if you can really verify that I'm not authentic, or this message is not authentic, then you will not accept it. And in that case, you will not corrupt the communication. That's what we want to do. Okay? What about the replay attack? Question.
How do you authenticate it?
Can you actually authenticate it?
Would using replay attack in message authentication?
You can authenticate.
No, because authentication here means that with the message, you have to send something to make sure that this message is authentic, regardless of this thing. Okay? We'll talk about this now. That's the main topic of today. Okay? But let's assume that this message is authentic, which means if I do any alteration here in the message, you can easily detect that this is not coming from me, and this modification is not authentic. So you will throw it away. Okay? So how about me being smart and say, okay, so I will take the message as is with the authentication and everything, and after a few minutes I can just play it as is and give it to you.
It depends on implementation, but message authentication part should be generated at the time of generation of the message.
Message authentication, by the way, does not have anything to do with the time of the message, unless you have a protocol level information here that you have any kind of timestamp or sequence number. Okay, so if you have here some kind of a timestamp or a sequence number, then you can easily detect that replay attack. Okay, so message authentication itself will not help you, will not protect against the replay attack, but you can easily do that at the protocol level. Okay, طيب. So we can have two ways of authentication. We can use conventional encryption techniques because, well, you can think of encryption techniques as a way to authenticate. Why? Because only the two of us, we share the key, right? So if I can make sure that this key is somewhat embedded in any communication you send to me, then I can say that this is actually coming from you and not anyone else, because I know that no one else has this key. Okay? So in a way, conventional cryptographic algorithms can be used for authentication as well. But we will see how we can do that. So symmetric encryption alone is not suitable tool for data authentication. We'll see why. So we assume only that the sender and receiver, they share the key. صح. So the genuine sender would be able to encrypt and the original receiver will be able to decrypt. Right. But the receiver assumes that no alteration happens. So if I send you an encrypted message, and an active attacker modifies this encrypted message in the middle, okay, the receiver will not recognize that this has been modified. right? So the receiver would decrypt the modified message as if it's a legitimate message, which will force the receiver to decrypt totally something else other than what I have sent. Which means that encryption on its own can be used for authentication, but it cannot be used for integrity checks. It cannot prevent the modification attack or the injection attacks. Okay? So if the message includes a timestamp, the receiver assumes that the message has not been delayed beyond that normally expected for the network transit. So any kind of modification to the message, the receiver will not be able to detect it and will decrypt the message as if it's a legitimate message and will get something else. So encryption might be needed, but it's not sufficient. Okay? So it can perform part of the job, but not the whole job. It can perform the authentication part because the encrypted text is highly based on the key. Okay? So if I decrypt the message and it was not modified, then somehow I can authenticate that this is coming from you because only you and me have this key. So without the message encryption, also there is a big disadvantage in this part that encryption techniques are somewhat expensive. They are computationally very heavy. Okay, so we will see that most of the protocols they try to avoid using encryption for authentication. For confidentiality, you kind of have to, but for authentication, it's not the common way. So authentication tag is generated and appended to each message, which is what we have shown. So usually the authentication happens by performing certain operation on the text. Okay, it could be encryption. But rather than sending the encrypted version only, we will try to do certain encryption and append it with the message and send both of them. Okay? Why? Because the encrypted value will be highly based on the actual text. So in the authentication, by the way, there is no requirement for reversibility. As we will see, we don't have to decrypt the appended message to get to the original message. No, that's not a requirement. What we want to do is to verify that the message, the content itself has not been altered. So at the receiver side, what I normally do is to take the actual message again and try to reach to the same tag using the same procedure. If I reach to the same tag, then the message has not been altered. Okay? If I reach to another tag, then this is an indication to me that the message has been modified, and in that case, I will have to throw it away. I will not accept it. Okay? So for that tag, this tag, we can use a modified algorithm based on encryption, as we will see, or we can use a specially made algorithm for this. Okay? So we will talk about the cases. So that's what we talk about here. So this is the message. This is the actual message. So we will feed that to a Hmac algorithm, and this Hmac algorithm could in fact leverage encryption, or could be a specially made algorithm to generate that Hmac. Okay? And then we append this Hmac with the message. The idea is not to reverse it on the other side at all. That's not the idea. To get from the tag we reach the message. That's not the idea. The idea here is that this tag preserves the integrity of the original message. So when it reaches to the receiver will have to get the message and try to generate the same tag using the same Hmac algorithm, the same Hmac procedure. If the generated Hmac is the same, then that's a verification that this message preserves integrity. Okay? So that's what happens at the receiver side. But reversibility is not a requirement here. Okay? Synchronization. There is no issue with synchronization here because remember, this is not like an arbitrary sized stream of this. The message is of fixed size. It could take different sizes, but at the end of the day, it's limited in terms of size. Okay? This Hmac is fixed size, and we'll see how from arbitrary sized message we get a fixed size Hmac. Okay? So we send this as one unit on the other side. So on the other side here, we take the same message, and then from this message we generate the Hmac, and then we compare it. You see? So there's no issue of synchronization. In stream cipher, the problem is you will have to from the pseudo random number generator, you have to generate random sequence at the sender and random sequence at the receiver. Okay? So if there is any misalignment in the speed of generating these random bytes, that's when the synchronization issue happens. Here, there's no such thing. There's no synchronization issue. Okay, type. So this is message authentication. Okay, but remember, بقى this Hmac has two purposes now. It works as a digital signature for the message. Okay, to preserve the message integrity, but it needs to also maintain certain identity for the sender. Okay? It needs to also maintain certain identity for the sender. To embed here somehow the fact that the sender who sent this message is person X, so that when the receiver here, he knows that he uses that key, the same key that the sender uses. Okay? If we use the same key, then this is somewhat a way for authenticating each other. Okay? So the key with the Hmac algorithm embeds this key in the Hmac, and if I have the same key, I will be able to generate the same Hmac. So if the key is different, so assuming that there is an active attacker who tries to impersonate himself as one of the sender or the receiver, if he does not have that key, then he cannot really generate the same Hmac because he has a different key. Okay? So we can easily identify that that's not a legitimate user because he does not have the key that we expect, because the key is shared here on both sides. Okay? So this Hmac acts as two purposes. One, it preserves message integrity, which means it protects the message from being altered. And two, it authenticates the sender by somehow embedding the key into this Hmac. If we don't do the key embedding, then it's some kind of a signature for the message only, but it does not perform the authentication part. And we'll talk about this. So actually part of today's lecture is about the digital signatures, which is not a Hmac in this case, which is not used for message authentication. It just preserves the integrity, but it has nothing to do with the authentication. So if we want to add the authentication with the digital signature, then we have to use some Hmac message authentication algorithm. Okay? Message authentication code algorithm. It's not a physical address, عشان بس الناس network. Do not confuse that with physical address. Huh? MAC here is message authentication code. واضح؟ طيب. The one way is to use hash functions. The problem with hash functions is that they are not key-based. They don't use keys. So hash functions can be used for generating digital signatures, but they cannot be used for authenticating a user. Okay? So why do we have to talk about it? We can talk about it because actually we can use hash functions for the integrity part, and then the key we can use something else like encryption, because we said in encryption techniques, they can in fact be used for authentication, but they cannot be used for integrity. Okay? So if somehow we can integrate the hash with the encryption, we can do both. Okay? So this is the first approach. The first approach is to say, okay, so let's just use normal hash functions as a way to generate digital signatures to preserve integrity. Okay? And then we can use the authentication through encryption techniques later, using the key. Right. What is the main objective of the hash functions? The hash function accepts any variable size message, any size. So again, the input message could be of any size, but there is a limit, there is a boundary. We'll talk about it. And it produces fixed size, so no matter how long your message is, the output is the same. Which essentially means that the message digest, okay, it's actually a combination of all the parts of the message. Okay? One very, very simple example of this, we studied in Network 1. Parity bits. Parity bits is somewhat a combination of, so we can take a packet, a very big, long packet, we can, stack it up in terms of words of 32 bits. You can have as many 32 bits as you want, right? And just take XOR, 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 right? So we calculate parity bits, okay? Of course, if the message is not divisible by 32, we know what to do. We do padding, very easy, right? So we know how to do that. But is this good in terms of message digest? No, we'll see why. Okay, so CRC or parity bits is not a good way of doing a digital signature, and we'll see why. It does not take a secret key. It does not take any key. Okay, this is the problem now. So it cannot be used for authenticating the sender, authenticating the other party. It cannot be used for that. So it can only be used for as a digital signature, just to preserve the integrity. CRC, theoretically speaking, it is considered a hash function, طبعا. But is it a good hash function? Because again, we'll talk about hash functions. Yes, you can have good or bad, similar to symmetric encryption techniques. There is a strong one, there is a weak one. Okay? Of course, parity bit is the weakest hash function you can ever have. We'll talk about why. It's very, very easy. Yeah. Type. To authenticate by a message, the message digest is then sent with the message. Okay, we know how to do that. But then we can encrypt the whole thing. Or we can do some kind of encryption to authenticate the user using the key. That will be a separate step. We'll see how to do that. Right. So with that, there are 3 ways that we can use this message digest or the hash function, okay, and complement that using the key to produce an actual MAC bound. The MAC in that case will do the 2 objectives we talked about: preserve message integrity and authentication. So One way, very straightforward. So using conventional encryption techniques, what we could do is to say, okay, so we'll take the message, we'll perform the hash, okay, which will produce a fixed size message digest. We cannot call it a Hmac, right? Because it's not based on a key. Then, as a second step, we apply an encryption technique only to the message digest, okay? Using the key to produce that. This one, we can call it a Hmac. Now we can call it a Hmac. But this is a message digest or a digital signature, we can call it. We cannot call it a Hmac, okay? That Hmac will then be added to the message. So as long as you have embedded the key into that, so somehow you can authenticate by the user, because supposedly only the user or the sender knows that key. Only the two of us will share that key. Okay? So that's one way of doing it. This is a step or one way. The second way is using public key encryption. And instead of using the shared key or the symmetric key, where the key in that case is shared and it's the same. For public key encryption, we use private key, okay, at the sender and the public key at the receiver. So that's another way of doing the same thing. The only difference between asymmetric or public key cryptography and the symmetric key cryptography is that for public key cryptography, you have two keys. If you use one for encryption, you have to use the other for decryption. Okay? You have two keys, two different keys, but they المفروض they work in pairs. So you cannot use any two keys and say, okay, one is used for encryption. No, here reversibility is important. So in order to be reversible, public key cryptography talks about the fact that you use one key for encryption, the other for decryption. Okay? The question is now, No. For public key encryption, one is private, one is public. And by private and public, the main motivation behind public key cryptography is actually the key sharing stage, which we did not talk about until now. We keep saying that sender and receiver, they share the key. How can you do that? How can you do it? They share the key. Okay, and if you ask me how do they share the key, I'll tell you, okay, the key is shared through a secure channel. It's a chicken and egg problem. So we are trying to secure the communication, but in order to secure the communication, we need another secure channel to share the key. We can break that channel, aslan.
We can use that secure trust and transfer the message.
Yeah, so that's why a big motivation behind public key cryptography is the fact that the key sharing in that case is much easier because you have two keys. One of them you can make it public, you can share it with anyone. Okay? So this one is easily shared. But the other one is private. So that's why, pay attention to this bar. For public key cryptography, we can use it for confidentiality or not. Public key cryptography, we can use it for confidentiality or not. We can, صح? What do we use for encryption?
The private key. Give us a scenario. So on the sender, I have a message, I'll encrypt it using the...
For confidentiality, you always use the public key for encryption.
Yes.
Nobody
Okay.
can.
Encryption happens with the private key on both sides.
Yeah, so if I want to secure a message and make it confidential, okay, and I want to send it to a person, then I use the public key of that person.
Yes, my private key will...
Then when it reaches that person, he will locally use the private key to decrypt. Okay? So for confidentiality, you use the public key for encryption and private key for decryption. For authentication, it's the other way around. Why? Because a person who is trying to authenticate himself, he should use the main identity of himself. what is the main idea? Public key is مشاعة. Everybody knows it, so it's not something يعني innovative or new. Huh? So the private key should be the one that's used to identify the person. Okay? So this is the private key. It's used after the hashing to encrypt the message to send it. If you use the public key of that person and you generate the same digital signature, so that's good.
You can also use the same technique to share symmetric key in order to establish the communication between two.
That's a good point. Sometimes they use the public key to share the shared key. Yes, actually, typically, in many communication systems, that's what happens. Yes, that's in many cases, that's what happens. So using public cryptography, you can easily create that secure channel with very minimal sharing, and you can use that secure channel to share the symmetric key. That's what typically happens.
We prefer symmetric actually, it's less complex, so less resource.
Bravo, Ali. Yes, in many cases, symmetric key is much less complex. And we'll talk about the complexity of public key cryptography next chapter, inshallah. Actually, in this chapter, that's later on, maybe next lecture. Okay, طيب. The problem with these two ways is that both of them, they use encryption. Can I achieve the same objective without using encryption? Why? First, because encryption is complex. Encryption is very complex. Can I perform the same thing without using encryption? And the answer, luckily, is yes, you can. Okay? So if you remove encryption altogether, so we can embed our identity together with the message. Okay? So this, we call it a secret value. Why? Because a key is associated with the word encryption. But here we call it any kind of secret value. So you and me, we agree on any secret sentence or any secret value, okay? So I will send you this secret value with every single message that I send you. Okay? But again, sending the secret value on its own will not preserve the integrity. But luckily, we can use hashing to preserve integrity. So the secret value, together with the message, will pass through the hashing function. And then we can call this a Hmac in that case. Why? Because it embeds inside this the identity of the sender. Okay? Using this way, it's much lighter in terms of complexity because I'm not using any encryption. And in fact, this is the most common way, as we will see later. IPsec, TLS, all of them, they use this. Most of the protocols, actually, they resort to using this simple. But of course, in that case, the secret value is the key. And through the communication, we have to share some key. Okay? So we might use that key as the secret value. We can do that. But the book prefers to use a secret value because a key is associated with encryption, but here it could be any secret value. You and me can agree on كلمة السر, some password, anything, any kind of secret value that we can communicate to each other, and we can embed it in every single message we send to each other. If we can do that, that's a way of authentication. Okay, any questions? So these are the three ways how we can get from hashing to Hmac. Okay? Using encryption or not even using encryption. We can go back and talk about secure hash. Okay? Because we know now how to use the hash for Hmac. That's a later stage. But let's talk first about the hash itself. So it's important to not only in the message authentication but in digital signature. So the hashing itself is useful on its own to produce some kind of a digital signature or a message digest that is a combination of the original message, so that if you change the message in any way, this message digest will not become valid, in which case I will know. Okay? And again, for hashing function, reversibility is not required. I don't want to, or I don't aim to go back from the hash back to the message. In fact, one of the requirements is that this should be very hard. Because if it's easy, then it's not a good hash. Okay? So the purpose is to produce some fingerprint of file, message, or any other arbitrary value data. To be useful for message authentication, but we need to preserve all these properties. And just focus here. These properties are very important, especially the last 2 or 3 ones. So a hash can be applied to any block of data of arbitrary size. So by changing the size of the message, I don't want you to tell me that, okay, the message digest will change its size. No, it should be fixed size. H is relatively easy to compute for any given X, making both hardware and software implementation practical. Because we know that for some encryption techniques, especially like this and triple this, it's very difficult to implement these techniques in software. Okay? But encryption on its own is a very complex operation, and we know that. That's why we came up with AES, and AES was much less complex. Here, we're just doing hash function, so the requirement here is that this should be or must be software friendly, so it should be implemented in software easily. Type. Number 4 بقى very important هنا بقى. For any given code or message digest H, it is computationally infeasible to find X such that Hx equal to A, H of X equal to H. Okay? Yani if I give you a message digest, okay, and even if you know all the alphabets and yani all the alphabets that constitute a message, okay, you can do all kind of combinations to a message to produce this value of the message digest. This should be computationally infeasible, which actually not only makes the reversibility not a requirement, it should be really hard. Otherwise, if I give you a message digest and you can construct somehow the original message, that's not good. Okay, so reversibility is not actually needed, and it's not. It should be very, very hard. Number 5 goes beyond that. So for any given X, if I give you X, it is computationally infeasible to find Y. And if I give you a message X, okay, let's say that X is actually a plain text, and the attacker gets X, okay? Because we said that this should be protected from any modification, okay? So if the attacker reads the message with the message digest, by the way, this could happen, right? Unless you use some kind of encryption on top, but this could happen. The attacker can get the message itself and can get the message digest. Okay? So he can say, okay, how about modifying the message itself in such a way that will preserve the message digest to remain as is. That's what this talks about. Okay? So that should be also computationally infeasible. And when we say computationally infeasible, does that mean impossible? Why is it theoretically always possible to generate 2 messages with the same digest?
Because the hash the collision point. So
Why there will always be collision. طبعا احنا what we try to do here is we try to make the collision hard. Collision means what? Two messages produce the same message digest. Okay? Two messages, h of x equal to h of y. That's collision. Okay? Why does this always happen? يعني, there is always a collision, no matter what you do.
Because we can calculate all possible values. It's infinite. So,
One possible value.
So it's prone to happen at some point.
Because the size of the messages being done.
Go ahead. You.
The size of the message is bigger than the size of the digest.
So,
the number of bits is smaller. So there's this amount of message that can be.
bravo. Yeah. That's a perfect answer. So the x and y, they have a length of, let's say, m. Okay? The message digest has a length of k, which is definitely less than, in fact, it should be much less than m. Okay? So the only way you can have absolutely no collision is k has to be equal to m. Right? Because let's assume that these are binary numbers. Okay? So if you have a length of m, what are the possible combinations of the message? 2 to the power m, right? These are all the combinations of the message. What are all the combinations of the message digest? 2 to the power k, right?
Yes.
So the only way you can have absolutely no collision is that the combination should be the same, so that it would be 1-to-1 mapping, right? As long as you have k less than m, so you will always have two combinations in the message that have the same message digest. That has to happen. واضحة دي ولا مش واضحة؟ You have to have two messages having the same hash. No matter what you do, it will happen. Okay? And I will show you a very simple example in the next slide. Which means that collision exists. A good hashing function, okay, tries to make that collision hard. Because it always exists. Okay? So the only thing I could do is just to make it as hard as possible for you. Okay? And now, again, I will show you a very extreme example based on the parity bits that we talked about. Okay? طيب. So this is the most important. So if I give you a message x, and you can easily perform some permutation on x such that the tag stays the same, تعرف على طول this is a very lousy hash function. This is not a secure hash. It's not a secure hash. Okay? واضحة دي? So in general, but to make this general, okay, so it is computationally, again, infeasible to find any pair of x. So here, I give you x, you modify x to get y. But number 6 here talks about, even if I don't give you x, it's very computationally infeasible for you to find any two messages that have the same hash. Okay? Does that exist? It does, but I'm just trying to make it as hard as possible for you. But you can always use brute force attacks to get these two messages. Okay? You can always get it. It's just that it's computationally hard. There is a theory called the birthday paradox. It says that the number of computation, assuming that the hash is of length n So usually it's breaking that or getting collision is in order of 2 to the power n divided by 2. Okay? These are the complexity of how you can get to a collision. So this, of course, assumes that the hash function is strong hash function, which means that it does not make that collision easy, because I will show you about one for this. So one simple example in the next slide, which is the parity bits. So there are two approaches, of course, to attacking a secure hash. If we know any vulnerability in that hash function, then we can rely on this and use cryptanalysis. And I will show you a very, very simple example for this. Of course, in that case, the hash function is not secure. It's not a secure hash function. Okay? A good secure hash function will again leave no room for the attacker to use anything but a brute force. And even with brute force, as we said, you can reach the collision using O of 2 to the power n divided by 2. There is a theorem for this that we don't have to get to, but it is possible. It is always possible. So that's an extreme example for a hash, which we cannot call it secure hash, of course. We can use this for detecting certain types of errors in communication, but definitely we cannot rely on this as a secure hash by any means. So this talks about CRC or parity bits, that we can generate a fixed hash code based on any arbitrary sized message, which is multiples of, let's say, n bits. N bits could be like 32 bits or something. So all I need to do is just to stack up all the 32 bits on top of each other, and for each column I just do XORing. Which means that if the number of ones here is odd, the value here will be 1. If the number of ones even, the value here will be 0. And I will do this on all the columns like this. That's one way of hashing. Can we call it secure? No. Why? The property that we just talked about, I can do it easily. So I can take any combination of these bits, as long as I preserve the number of ones to still be odd or even, I can do whatever combination I want. Okay? And all of these combinations, they will produce the same parity bit. So either 1, 1, 0, 0, 0, or 0, 0, 1, 1, or whatever. Okay? I can make the ones in any place, and it will still produce the same hash. Okay? Can we call this secure? Of course not. The properties that we just talked about are not really precise. So I can easily use cryptanalysis in that case to perform some modification to the message and cause collision, which means I can break the integrity of the message very easily. Okay? What happened? Any questions? Type. With that, some examples of hash. The secure hash algorithm was developed by NIST and published as Federal Information Processing, the FIPS 180. FIPS 180 in 93, they published the first hash, which was based on a technique that existed before the SHA, which is called a MD4 or MD5. So that technique existed before, and NIST has based the implementation of SHA based on that to produce the first hashing standard for SHA-1. We call it SHA-1. Okay? So that used a specific length for the message digest. And then later on, that produces 160 bits of a message digest, 160 bits, okay? بعدين in 2005, the NIST, they found that because again, we said that breaking for brute force, it's based on the size of this message digest, right? So if it's 160, so we can, in fact, use brute force in order of 2 to the power 80 operations to break this and cause collision, okay? And this is possible nowadays, so that does not indicate that SHA itself is vulnerable, but NIST, they have anticipated some possibility that this might be computationally reasonable to break and cause some collision in the near future. So they tried to be proactive and came up with SHA next generation.
Is it that with the hash function, it's not only the size of the key, I mean, in the public space, it's the time, how long they are used. Because besides brute forcing, you can use rainbow tables that is. So if a certain algorithm is for a long time in the public use, it provides the capability for the attacker to generate very large rainbow tables, which increases or decreases computational force that you need to break certain things.
Well, see, there's no key here.
I understand, but what I'm saying.
And the SHA itself is public. The algorithm is public. Everyone knows it.
Yeah, but when you are attacking hash functions, you are not using only brute force. There is a rainbow table
Right.
attack as well.
Right.
So if
Right.
there is a longer time presence of the hashing algorithm in the public space with a certain key length, it gives
With a
more
certain-
time.
with a certain-
certain
Hash length. Yeah.
It gives the capability to the attacker to generate more and more rainbow tables based on this hash
Right,
which
right.
decreases the time, computing time to find the message or to reverse the hash.
Well, the idea is not to reverse, you cause collision. To have two messages having the same hash.
Not only that, you know that many implementations use hashing to protect the passwords using salt.
Right.
But still, to find the password, if you have rainbow tables that are large enough, it becomes very fast.
I look forward to your seminar, really. I know, I see that you, mashallah, you're very knowledgeable in the field, and it looks like you have hands-on experience that does not exist in many places. So you're very much knowledgeable with the implementations of the different algorithms. Myself, I'm not like an expert with the different implementations and this and that. As I said before, in the first day, I'm not the security guy aslan. I'm just trying to learn the theory behind these techniques. So you will see that some variations of these implementations, and they are used in different places and for different usages and stuff. And I'm not aware of all of this, to be honest. But it's possible. So in any case, the NIST in 2005 tried to be proactive. Again, not that they discovered any flaw or any vulnerability in the algorithm itself, but they kind of anticipated the fact that, again, as he said, if that algorithm with the same hash length stays in public for a very, very long time, so this type of computation will be practically very, very reasonable, and everyone will be able to kind of break the algorithm. And breaking the algorithm here means that you can, with reasonable amount of computation, you can generate two messages with the same digest in a reasonable time. That's what that means. Okay. So they tried to come up with SHA-2, and SHA-2 has different sizes. So they said, let's try to be quantum proof as much as possible. So we try to make the hash size in different sizes so that depending on your application and depending on the security level that you want, you can increase the size of the hash and make your system more and more secure. But of course, the more hash size you get to, the more complexity you have to use in order to generate this hash every time. Okay? So this table kind of summarizes of course, this is SHA1, and all of these are SHA2. Okay? All of these are SHA2. So SHA2 starts from 2 to 4 bits of hash. And it could be 256, 384, and 512. Okay? So these are the sizes of the message digest that gets produced from this hashing algorithm. The message size, as we said before, it could be of any arbitrary size. However, in the standard, they put some limit. They put some limit. It's not that to say that the message has to have this length, but there is a boundary of the message size that makes the implementation of this message or this hash algorithm efficient, okay, and secure, طبعا. Because if you fix the hash size and increase the message a lot, you increase the probability of collision, of course. So you have to have a limit. طبعا these parameters these are implementation dependent. So there is a high correlation, or there's a relationship between the block size and the message digest, as we will see in a minute. So this block size is how you take the big message and divide it into blocks. When you divide it into blocks, you divide it into blocks with fixed size. Okay? But the number of these blocks is varied. واضحة كده؟ Similar to what we did for the parity bits. For the parity bits, we divided the message into n bits, but you can have as many of these blocks as you want, right? So that's the block size. And there is the word size as well, which could be 32 or 64, the word size. And of course, the number of steps. Number of steps similar to the rounds in the encryption. In the encryption, we talked about rounds. In this, we talked about 16 rounds. In AES, we talked about 10 rounds and so on. Similarly, here we also use some kind of steps or number of rounds. This is what I mentioned about the paradox, the birthday paradox theorem, which highlights this as the number of computations you need for brute force to cause collision, because it always exists. It's just that how much time you need to get to that collision. This is what we need to make it as high as possible. Okay. This table, so that's how the SHA 512 looks like. So what you do is that first you take the message of any arbitrary size, which is less than 2 to the power 512 or whatever. And then, of course, the first thing you do is that you have to break it into blocks of size 1024. Okay? Type, if the message itself is not divisible by 1024, what do? You do padding. But here padding, you do padding, but with the last 128 bits preserved to store the length of the unpadded message. واضح? So you have to put the length of the unpadded message. So basically you pad the message with the remaining such that this block is 1024. سهلة. واضح? Padding is fixed. You put 1 and then all zeros. As many zeros as you want. But such that the full message length, okay, with the length of the message itself as 128 bits, all of it is divisible by 1024. Once you do that, the steps is based on, again, blockchaining, which we did not explain for cipher blockchaining, we will explain here. So basically, we take each block, we pass it through a function. Remember, this block is of size here 1024. Okay? Then we pass it through a function, and this function takes the hash from the previous step. Okay? The hash from the previous step. The hash from the previous step here is, this one is 512, is of size 512. So this block is similar to the round function, if you remember in AES. So this is a function, but here it's not based on permutation and transposition. Here based on certain XOR combination of the input and of the two inputs. Yeah. Okay. So basically, what you do is that you take that block and you use that hash to kind of do some shift or circular shift. And then every time you XOR number of times, specific number of rounds, and that's it. These number of rounds are the number of steps that we have displayed in the previous. In any case, we will not get to the details of this. And in fact, this embedded function can be replaced by any other function. In the standard, they don't dictate a certain function here. Anyway, so what we do is that this function will output here something that's 512, of size 512. واضح كده? So this will get XOR'd or added to the previous hash. So basically, this operation, we can simply say that the HI is in fact the addition of two things. One is a function of the, sorry? MI and HI minus 1 added modulo addition with HI itself, or HI minus 1. Yes, HI minus 1. Of course, yes. Okay, this is what we call a blockchaining. Blockchaining is done through pipeline. So, as you can imagine here, this is the ultimate output that we want, this one. Okay, this is the output. And this output is based on all these other steps. All these chains of blocks. If we do this, طبعا, again, once we do this, this reminds you of what we did for the symmetric encryption. As well, if you can produce this simple equation, that also can be used for analysis for people again with information theoretic background to try to say, okay, so given this, I can come up with the birthday paradox and say that, okay, so computationally you can cause collision using these numbers. They produce this from that. So this equation is very important, and it's actually one of the requirements of any hashing algorithm. It should be hard to cause collision, but it should be easy to understand. Okay? So putting it in that structure makes it easy to understand for anyone, and you can map it using simple equations that allows people doing some analysis to do their analysis easily. They understand what's going on. Okay? Any questions? So enough, we can break for prayer? Okay, we'll go on for another 15-20 minutes or something, and then we'll switch to the seminar, inshallah. So this is with regards to the hash. Now, as we said before, hash only performs the digital signature, but it does not produce Hmac. Okay, so the standards that uses hashing for producing the Hmac is called Hmac. Okay, so hash-based message authentication codes. So Hmac uses the hashing and uses the key or the secret value, as we have discussed before, to produce the hash or message digest based on the original message and the secret value. If we combine the original message and the secret value, as we said, then we achieve the two objectives, which is authentication and signature. Okay? So there has been an increased interest in developing Hmac derived from cryptographic hash code. Okay? Like SHA. Why based on hash codes, and why not, for example, using the normal cryptographic techniques like symmetric encryption? Because as we said, symmetric encryption is very complex in terms of computations. So they use, or to avoid using the cryptographic encryption techniques for authentication should be the way to go if it's by any means possible. And using Hmac, luckily it's possible. So cryptographic hash functions generally execute much faster in software compared to DES and triple DES. And that's a fact. Especially DES, as we have discussed before, it's pretty much, it has to be done in hardware, pretty much, based on the fact that it's based on bit level operations, and that makes it more suitable for hardware implementations. Library code for cryptographic hash functions is very widely available, starting from MD4 and MD5 and coming through SHA1 and SHA2. There are very efficient software libraries that are very widely available, and we can use it. So there have been a number of proposals for the incorporation of secret key or secret value into the generation of hash. If we can do that, then we achieve the message authentication together with the digital signature. Okay. So that's the approach of Hmac. So Hmac is based on hashing, but incorporating the secret value, or in that case, the key, the shared key. Okay? So Hmac has been issued or produced first by IETF, not by NIST. Again, you don't have to memorize all these things. You don't have to memorize FIBS 180 and so on. You don't have to do this. But this is just for people who are interested in historical events. These numbers are there. It has been chosen as the mandatory to implement Hmac for IPsec and for different layers of transport layer security. Okay, so Hmac, we will mention Hmac a lot later on in part 2 when we start to talk about the network security protocols. We'll mention it a lot. Right. So to use, so the objectives of Hmac is to use without modification available hash function. So we don't want to complicate the hash function a lot to introduce authentication. Okay? So by incorporating just a secret value and hashing the whole thing, the added computation is not that significant, right? Rather than saying, okay, so we'll produce the message digest and then we'll use encryption. That's a significant additional computation added. So Hmac tries to minimize this additional computations by using the concept of secret key. ماشي? To allow for easy replaceability of the embedded hash function. So this F function, okay, can be replaced. So on one hand, this F function makes the analysis of the hashing technique easy. Just by performing the equation, in simple equation, we have been able to model the SHA 512, right? Using one simple equation. Okay, but this embedded function can be replaced by anything. To preserve the original performance, as we said, of the hash function without incurring any significant degradation, and that's what we have achieved by avoiding encryption, and to have a well understood cryptographic analysis using very simple equations. We have been able to model the SHA 512, which will be easy to understand, and for analysis people who are interested to derive some boundaries and generate this birthday paradox and all of this, they will be able to do that because everything is understood simply by equations. So this is how we do Hmac. So remember, Hmac is nothing but to take SHA and just embed the key, right? So ideally, we can say, okay, so let's just add the key to the message and create the hash.
Yeah.
That's not what they do, unfortunately. They have to introduce some level of complexity a little bit. So what they did is that instead of embedded the key as one unit, what they did is that they apply iPad and OPAD. An iPad and OPAD is nothing but masks. Okay? Once you put this mask to the key, it's like you get the leftmost part and the rightmost part. So in the leftmost part, you put it as a secret value with the message, and then you apply the hash. And of course, H0 is the initial vector. H0 is any arbitrary. It's a fixed value, by the way. In the book, it's I think it's 128 bits or something like this, which are predefined. These are predefined value fixed. They are generated from prime numbers and so on and so forth, but it's fixed. Initial vector here is fixed. Okay. So this is H0. We use SHA, normal SHA, to produce n bits, 512, for the case of SHA 512. And then we take this message digest, which is fixed size, because the message here is arbitrary size. We convert it to 512. And then we mask the other part of the key. And then we add it and we do hashing again. So the only difference is that we do hashing on two different steps. But luckily, the second stage of hashing is done on the 512, which is, again, is less complex. So to do these two steps, the added complexity on top of SHA is not that big, as you can imagine. So the only thing we did is that we embedded that key on two steps. That's what we did. ماشي؟ مفهومة كده؟ واضحة؟ So iPad and OPAD, they are nothing but masks. They mask part of the key, and they apply the key on two stages.
Do you use the same idea in both fashions?
In both?
In both terms of fashion?
Yes. Here, SHA, both.
No,
are
but
the
I'm
same.
saying ID, the initialization factor.
Initialization vector? That's what it seems, yes. That's what it seems. It's the same. Yeah. I don't think there is any issue with that. Okay. So this is the Hmac. So by embedding the key in the hashing, we can do authentication with the digital signature. Okay. Of course, what we definitely try to do through Hmac is not to do this in Cmac. In Cmac, what we want to do is to use hashing, but in that case, with encryption. Okay? So the alternative, if we don't use Hmac, again, using some analysis and experiments and stuff like that, people nowadays, they highly prefer Hmac over Cmac. Why? Not because of the level of security, because it seems from the analysis that both of them are highly unbreakable, okay? So in terms of security, they are both equally secure. But in that case, of course, we should select the one with the more efficient complexity or less complexity. And in that case, Hmac by far is less complex. So Cmac, what it does is that we did that before, in the beginning of the lecture. So we use the M1, and then we do the block chaining here, and in each step we do the encryption using the key, and then we use that in the next step, and the next step, and the next step. So we do, this is what we call a blockchain. Okay? So this is the, here in the book, they talk about two, and I don't know why, maybe you can give us some hints here or some idea why, but in the book, it says there are two cases here. One case, if the message is integer multiples of the block size, because this is the block size, okay? If the message itself is multiples of the block size, integer multiples of the block size, in which case we don't have to do padding, yani. Okay? So in that case, we use the chaining, but then we use K1. And K1 is a sub-key which seems to be dependent or sub-key generated from the actual key. Okay? But if the message is not integer multiples of the block size, then we use padding as we did before, but in that case we use K2, which is different from K1. No, well, it's if the message is multiples of the block size, we use K1. If the message is not multiples of the block size, then we use K2. Yes, K1 is correlated or is generated from K. Both K1 and K2, they are both generated from K. And then based on the incoming message, if the incoming message is integer multiples of the block size, then we use K1. Otherwise, we use K2. Why? I don't know. Eh? Yes, of the same size. Yes, same size. Yes, same size. Yes, same size. Yeah, so, and K1 and K2, they are used as the very last step, by the way. It's just XOR to the very last step. So, but why they use the two values, I don't know. You understand? And it's not mentioned in the book. Maybe I can look it up sometime. No. This is different message. If the incoming message has a length which is multiples of the block size, we use K1. Otherwise, we use K2. Okay, so that's what it is. Okay. In any case, this is the ultimate output that we use as for authentication and for Hmac. Okay. Okay. I don't know. Should I?